Welcome you all to this course on electron diffraction and imaging. In the last class, we looked at the kinematical and dynamical theory, okay, for contrast. Let's essentially look at how the intensity of the of the beam at every point on the back of the sample will be changing. That is what we are mapping as the image. Okay. You have doubt? That is, as the electron beam passes through the sample, okay, diffraction phenomena is occurring, because of which at every point you concentrate only on the transmitted beam. Okay. So, suppose diffraction is taking place at this point, intensity of the transmitted beam, amplitude if you look at it, it will be dependent upon how the scattering is taking place as the beam passes through. That will decide, and the square of that is going to give the intensity, correct. So, essentially from region to region, if you look at the back of that sample, there is going to be a variation in amplitude of the wave which is going to be there. That is what is manifest. We try to magnify it, and that comes as that image in the image plane, correct. That is how we get the image. Is it clear? Okay. Then we looked at how the dynamical theory, especially the concept of extinction distance, makes a lot of difference in the variation in contrast when the thickness of the sample varies. All those aspects we have considered, but that is all for a perfect crystal. Today what we will do it is that we will look at various types of defects, because in many classes I have told what are the types of defects which we can have in single crystals, what are the type of defects which we can have in polycrystalline material, okay. How contrast arises in defect, that is what we will look at it in the next 1 or 2 class. Okay. Okay. When we want to look at contrast from defects, the defect itself we can classify into 2 categories. Okay. One is like the defects which produce a strain field around them, that is one type of a defect. Give me an example. Dislocations. And second phase particle precipitation. Okay. Suppose bending of the crystal is there in some regions, that is also going to introduce variation in strain in the material. So, these are all the type of defects which introduce strain field around them, correct. Then the other type of defect is the defect which brings about the change in the lattices, shift in the lattices. What are the types of defects which we can, I say that defects without strain fields, that is what I had put it up. This could be some planar defects. What are the type of defects which we can have? Stacking faults, yes, right. Then antiphase boundaries, all interfaces, okay. Then domain boundaries, even thin precipitates, they can bring about some shift. Yes.
Bent crystal example.
Bent crystal is that, suppose we prepare a sample, TM sample. Normally there are many methods which are being used. The most frequently used technique or conveniently used technique is the jet thinning. Jet thinning, jet polishing. Okay. There what you are trying to do it is that you have a sample in which from 2 nozzles, okay, jet is coming and falling onto the sample, right. The sample gets thinned, finally this is how the sample becomes, which may be a hole which is coming at this point. Closer to the hole you have thin regions are there, right. When this jet falls itself, when the sample becomes extremely thin, even a small flow of the jet can bring about some bending in the, introduce deformation in the material, okay. That will introduce the unit cells which should have been perfectly flat, you find that there is a slight bending of the unit cell is taking place. That is, with respect to any particular origin, if you choose, the unit cell orientation has shifted. That also can be considered as a sort of a strain. Okay? Is it clear? So, these are all the types of defects which we can have. Okay? We will look at how contrast arises from the various defects in the microscope. To understand this contrast, the first thing which you should know is about what is the type of the defect which we have. Okay? And on the basis of, if we know about the type of defect, then we can find out what all conditions under which the defects will become visible, what is the condition under which the defect will not be visible. On that basis, we can formulate some rules for observing these defects, right? That is what is being followed to identify defects in the sample. Is it clear? So, if you remember, the last class we talked about both the kinematical condition, okay, how the intensity of each of the diffracted spot will be affected, right. So, that is essentially governed by delta k dot RLMB, okay, which represents the position of each atomic point in the unit cell. Okay. This value equals whether an integer or not, correct. When we substitute this value, delta k equals g plus s, and the defect itself can be written as position of each of the unit cell represented by a point which is called as RL, plus the position of atoms within the unit cell which is given by RU, plus deviation defect is RD. Okay. If you substitute this and all these things and solve it, then you will find that this is the sort of an expression which we will be getting it, correct. On that basis, and finally this has to be summed over the whole volume which we are eliminating, or with respect to Z, that is at each point if we try to calculate how the intensity is going to be there, that is the full volume is being covered, correct, and then the variation in intensity will come. And summation can also be changed into an integration, you know that, okay. That is essentially what is being done. And then we define that deviation which the defect introduces in the lattice is essentially what we call as the deviation parameter S, which is only along the Z direction which exists, correct. So, then this expression will turn out to be S to Z plus G dot RD, where G is the diffraction vector which you are using it for imaging the sample, okay, and RD is the defect vector. And then we mentioned that if this vector this product becomes 0, then it will behave like a perfect crystal, and if the product is going to be different, some value, then that will introduce some phase shift in the overall amplitude. This we considered on the basis of our kinematical condition using the phasor diagram, right. Now, that is what we will be employing it here to look at some of the intensity. Now, when there is a deviation, not deviation, this is with respect to kinematical theory. Under dynamical theory, what we considered is that the electron beam interacts strongly with the material, and that is a fact, okay. Especially at Bragg condition, both the diffracted beam as well as the transmitted beam contribute to each other. In such a condition, okay, if we write a plane wave, we can represent the electron. As it enters into the sample, okay, it interacts with the periodicity of the lattice, that is a potential which is going to be there, plus the wave also can be represented as a contribution coming from the various diffracted beam. Okay. This is how we considered it, and then we solve the Schrodinger equation. We get an equation of this type which couples how the diffraction amplitude, okay, that is the beam amplitude, varies as a function of depth, okay, which depends upon, if now you can see that it depends upon both the amplitude of the transmitted beam as well as the diffracted beam at every depth at the sample, correct. This coupled equation, when it has been solved, we are able to get the amplitude of the transmitted beam and the diffracted beam at the back of the foil, and on that basis only we could explain the fringe contrast which occurs in the case of a wedge sample. That is right. Okay. Then also I mentioned that if it contains a defect, okay, then what is essentially going to happen is that this SZ which is going to be there, this will be modified by this term also will come, the defect term also. So, this is how the equation will change, correct. Then the solution to this equation has to be found. So, using this also, that is either using phasor amplitude diagram which is for kinematical condition, or using dynamical theory, both of them could be used to find, get information about how the intensity of the diffracted and the transmitted beam varies at different points, okay, both in the perfect crystal as well as in the regions which contain the defect. Okay. Let us consider the case, because I mentioned that we will talk about first a planar defect. Okay, we will take that as an example. Okay, and as we discussed, the type of defects are antiphase boundaries. Okay, then stacking faults, interfaces between different regions. All these things are there. What sort of contrast which they will exhibit? That's what we look at it. Okay, this is how the amplitude which we are trying to explain. What is important is that now you look at this sample. Suppose a defect is there at midway, which has shifted the atom by some distance. So, essentially what we are considering it is, I am just showing the external form of the lattice. Okay, this lattice is being now shifted by some distance t in the x direction, you assume. Okay. Then when this has been shifted, the waves which are coming in here, and when they are scattered and when they reach here, okay, there is going to be an additional amplitude which will be created to this. Okay. That is essentially what we are trying to look at here. Okay. What is this which it is going to, how we can find out this RD is what it is the defect position, right. So, suppose this is the perfect position of the atom which is going to be there, okay, RD equals T, then we can write alpha equal to 2 pi G into T, it will turn out to be, right. This alpha itself we can write it in the, this term can be explained e to the power of I alpha, we can write it. Okay. If we do that, now the psi g becomes 2 times, one due to the deviation. Is this clear? Okay. Because essentially 2 term integral S is there I G dot R, right. This R we assume to be some translation which has been given to the lattice from the original position which is there on all the layers at the top. Okay. So, if we do that, and so this term itself can be written as what we are trying to do, it is into dz e to the power of I alpha. So, alpha will be equal to 2 pi G dot R. Okay. Depending upon the value of R which we choose, okay, the value of R is decided by the nature of the defect, that decides what is the vector. So, here we have chosen as some arbitrary distance where that lattice is just displaced in the x direction. Okay. Then to find out the intensity, what we have to do it is that first there is going to be we have to take the amplitude which is going to be there from up to this particular point where the defect is there. Then beyond that it introduces some variation in the amplitude, because everywhere there is a phase shift has been introduced. So, if we add both of them together, we will be getting what is going to be the amplitude at the end at every point. You understand that? Huh? See, if you have to find out the amplitude, how we are finding out the amplitude? What is going to be the amplitude up to this point? We can calculate it using this expression. Here, what is the value of, there is no defect which is present, so R will become 0, right? So this is what essentially is going to be up to 0 to, you take this thickness to be T1. Up to this we have done it. Now what we do it is that beyond this there is a phase shift which is introduced. So what will be the amplitude when the beam enters here? It is going to be this value. This from T1 to T you have to do that. The total sum is going to give what is going to be the amplitude at the end, correct? So the same thing can be represented in the case of a phasor diagram. In the phasor diagram what we are trying to do essentially is that we know G, okay, as we go along the beam in this direction, okay, the position of R is changing, so that the phase factor is going to change, though the amplitude remains that same, okay. Then what we are trying to do essentially is that to find out the net amplitude, okay, like this it will be going and like this, okay. If there is no absorption, it will be rotating around like this. This is the way that, and if at some particular point, at some particular depth, we have reached from here to here, so this vector gives what is going to be the net amplitude, correct? This is what the phasor diagram does it, okay. That way we can also do it. Now I am considering a case where the translation which we have introduced is 0. Then what will happen? Then essentially the phasor diagram will be like a circle which it will be propagating. This value of alpha will turn out to be 0, okay. Then the psi g, if we look at it, it is a perfect crystal. It is independent of the x and y position, whether I calculate it at this particular point or this particular point with respect to different x, y and the same, because x and y is defined on this region, right. This will be x and y will be, you take perpendicular to it. This is the z of the sample which we consider it, okay. Now let us take that case where this is the particular case where with respect to this top layer, at this point the layer is shifted by a distance a by 2, okay. If this is shifted by a by 2, what will happen to this value alpha will become pi into g. That means that if up to this particular point, if the amplitude of the phase you assume that it has reached up to this particular point, then this introduces a phase shift of pi by g, means that now for the next one from here when it comes, instead of going it from here to here, it will go from here to here in the opposite direction. Now it will again retrace it like this. And now on this point, suppose at some particular point here I wanted to find out, from here to some particular point I will have to look at what is going to be the net amplitude. That is how we have to do this calculation as far as the phasor diagram is concerned. Is this clear, how this phasor diagram can be used to find out the amplitude? Okay. Suppose we assume that the vector which we are using, this is a simple cubic lattice which we have considered, the vector g equals 1 0 0. Then what will happen to alpha value will become pi, right? Is it not? If alpha becomes pi, this introduces a phase shift which is reversal of this, okay. Now suppose the vector which I use g, okay, to image the defect equals 2 0 0, then what will happen to alpha? Become 2 pi. When alpha becomes 2 pi, what will happen to this? Then again it will go as if it is a perfect lattice. So even though there is a defect is there, okay, depending upon the g vector which you use it, that is specifically dependent upon the fault vector that decides for some g vector you find that in this particular case the amplitude can become reversal of it. In the other case the amplitude becomes.
So in the phasor there is no there is no direction, right?
No, the direction is there. This is the way direction I had marked it. You have to mark it.
Okay, so but not a lattice direction, right? There's no.
No, it is essentially, we are not looking at the lattice. The lattice, what it does, it introduces some phase shift to the wave which is scattered in the direction.
So G could be any vector, right?
Which one?
It could be a translation in any direction.
No, G vector.
Some other vector.
G is a reciprocal lattice vector.
Yes, but
diffraction vector which
any diffraction. Right?
Any diffraction vector.
So if it is 110, then what will happen?
You tell me if it is going to be 110, then what will become G?
We will take mod of G.
Yeah. See, here that value which you have to take, it is this RD which you are taking, it is in whichever units you take it. See, pi is in radian. So here when we write it, this one is for a by 2, this specific case. Okay. Otherwise what you have to take it is that G into G dot RD has to be a dimensionless quantity. Correct? Okay. That's what we will be doing it. Here we are considering as a specific case where 100, because essentially it is going to be I, na?
Yes.
100 also I, so I into I will becomes 1.
Yes.
So that's the way. Otherwise you have to take the this one, dot product. Okay.
Yes.
That's the general case. It's clear? Okay. Then when you do this, we find that it introduces some phase shift, correct? Okay. This is as far as a vector which is essentially at some particular depth from the sample surface which we have considered. It can so happen that this fault itself could be inclined with respect to the sample. If the fault is inclined like this in this direction, the T also is going to, so different points you will have. So what will happen is that some places they will all add together, some places they will subtract. So you will have a variation in intensity will come. Essentially it will give rise to a fringe contrast. That is, if some regions amplitude all add together, some places they subtract and become 0, okay, then you take the square of it. So as a function of distance when you do it, it is going to give rise to a fringe contrast. That is how all planar defects give rise to a fringe contrast. Is it clear? Okay. Now let us take another case. Okay. Suppose one crystal is sitting on top of another crystal, the lattice parameter is that same. That also case happens, that is, you have a matrix in which a precipitate is there. The precipitate also has got the same crystal structure as that of the matrix, you can assume, like gamma prime and gamma, or if you consider a simple cubic lattice, okay, in which we have another lattice with a slight lattice parameter difference, we can consider that. Suppose it is such that from here to here, when we consider it, there is a perfect matching of the lattice because a slight misfit is there. In between, the separation between the planes are going to change continuously. At some particular point here, it becomes midway. So now if we calculate that amplitude, what is happening is the vector with respect to xy position is continuously changing. So this will give rise to a variation in the phase, and finally when we look at the amplitude, okay, and the intensity will maybe here it will add together at this point because you do not see the defect, and at this midpoint it is an phase difference of pi, it will become, intensity will become 0. Here again it will become, though the lattice separation is large, now we are able to get a spacing of the amplitudes, the fringe spacing, which is much larger than that. And from that, from this now we can find out what is the separation between the two lattices we can calculate if we measure this fringe spacing.
The upper lattice.
Yeah. What the difference between them, that value. So if we know the value of one of them, then we can find out which one. All these things could be done. Is it okay? These sort of fringes which are coming are what we call it as a Moiré fringe. Okay. This Moiré fringe could be seen easily with our eye. I don't know whether you have noticed Moiré fringes. Okay. The simplest thing which you can take it is grids are there, na? Not these grids, even on the roadside, that jali for the window you put the grids, na? A very fine mesh is there. If two meshes of different sizes are there, mesh size, you keep one on top of the other, you look at it, then you will find that there will be a, this I think if you go to any of these science museums here, they will show this as for kids, one of these things. And if you rotate both with one grid with respect to another, if you rotate it, you will get a different type of a fringe pattern, you will be getting it. This is nothing but a Moiré fringe pattern because with the light which we are using it, okay. Because this is essentially a monochromatic combination of monochromatic wavelengths which we use it. With that we will be getting this sort of a contrast, okay. And here what will be the effect of this one? Suppose this is an one dimensional lattice which is going to be there. What will be the effect of this on the diffraction pattern?
So where the misfit is the maximum, you will have
No.
one.
So when the misfit is there, suppose this a central spot is there, you get one spot corresponding to the top layer. The bottom layer has got a lattice spacing which is small. Inverse of it will be in this one. So you will be getting one more reflection corresponding to that. Correct?
No, it didn't.
See, what does the G vector depend on? Lattice spacing of the planes in that direction. Okay. Suppose we have a crystal like this. For this crystal, there is a particular, here the spacing is large. So because of that, the G vector will be small. So I just mark this. This is origin and this is the G corresponding to a top lattice.
Basically the spots for the above part and the below part.
Below part will come. Because the beam is, because these are all parallel to each other. That is one, right?
Where are we seeing the fringe pattern?
Where are we seeing the fringe pattern is? So now when you have to take the image, what you do it is that you put aperture around this point because these separations are very small. So when you put an aperture, these two beams, they are monochromatic beams, okay? These beams are going to interfere. And when they interfere, they will give rise to a beat pattern. Interference pattern is nothing but a beat pattern. Huh? So here, that is what I am just showing it is that this is difference. Essentially, these are all simple, these ones. So the separation between them in the real spacing will be 1 by GTM. Okay. This you can calculate. This is how it will turn out to be if D1 and D2 are the spacing. These things you have to work it out. Okay. Similar thing which can happen with rotational Moiré fringe also. That is where if it is displaced, it's slightly rotated, then also we will be getting a fringe spacing corresponding to that. Okay. What I will try to do it is I will show some example. Now you see that when this is a fringe.
So if it's rotated, then the point will go a little up or something.
Yeah, it will go. Okay. This is with respect to what we have shown it with respect to one. I will come back to the one where it's a sonaxis, the beam is falling. Then when so many planes are diffracting, what it will happen. Okay. Is this clear? Okay. Now you see that it's slightly rotated, how the fringe pattern is changing. For this, you don't require anything else. What you do it is, you know what has been done here? It is only lines with two different spacings have been drawn. And if you look at it, actually it all lines with two different spacing, starting from here it has been done. When we look with our eye, it appears a fringe pattern, we are seeing it, nothing else. This you can draw any line on a piece of paper and look at it, you will observe this. You just superimpose one on top of the other, this pattern you will get it. Okay. And what is essentially important here is that suppose we tilt the sample, then when the beam comes, the diffraction planes may change, the separations will change depending upon this. These fringe spacings can shift here and there. So that is an indication that this is not a lattice fringes, because when you do high resolution microscopy you see some fringes. Na? Those fringes essentially correspond to separation between the atoms, because there are not two lattices, it is only one particular lattice at which we are looking at it. Whereas if a Moiré fringe is there, the Moiré fringe pattern, the spacings can change. Okay? And if you see here, this is a diffraction pattern which is taken, okay, for a beam which is passing along a simple cubic lattice, you assume to be passing along 0, 0, 1. Okay? Then, yes.
So yes, exactly. So in that Moiré fringe, the distances of the planes is changing, right, through the
Yeah.
line. So then basically how you get only one point, that point will be the
Okay. No, this is what I tell you. Here you say more point, how it comes. Suppose I assume that here there is another one. Okay. This is GT, and this one will be, I will correspond to a bottom crystal GB. Okay. Okay. Similarly, you will be getting one here and another one will come, right. This will be GT and this will be some value of G will come. This is how it should come, right. The two patterns superimposed one on top of the other.
It shouldn't be a one single point, right? Because the spacing is like linearly changing, right? At the edges it is equal, then the spacing is of the top. Okay, I saw
It is from two different crystals.
Yes, sir.
As far as for the Moiré fringe is concerned, only there is going to be a,
There are only two spacing.
because when we calculate that intensity down along it, it's going to be, but the same beam can give rise to, as it passes through a parallel beam, it will give a diffraction pattern from the top layer, a diffraction pattern from the bottom layer. Both are independently, which is coming very close by. But when we
Top
calculate
layer is
the
one spacing and the bottom layer is one spacing. That's it. There's
two
no
different
change in
spacings.
spacing.
No, that's not changing. But when those lattices are kept close to each other, okay, at some distance you find that
It will match.
some lattice planes will match at some periodic interval, that's all. Diffraction is taking place from each lattice separately. So this phenomena will give rise to a diffraction spot like this, which are separated. When we put an aperture around it, an interference fringe contrast is essentially from the top layer the beam which comes, and when it sees the bottom layer, the amplitude of the wave which is coming is going to change it. So the net amplitude, this is something like considering an interference essentially. Okay. And this is the type of a pattern which we should get it. If I remove all these G1, G2, and all these things, essentially we should have that is the inner pattern square corresponds to the top lattice, and the outer pattern, diffraction pattern, corresponds to a bottom lattice. But you know that when this is a strong diffraction in a zone axis, the diffraction beam also contribute to scattering, correct, in the forward. That means that the diffraction beam is now acting as a particular point as an incident beam, right. So then I can, what I can do it is with this as the point, another pattern which is corresponding to this one. So spots will come like this. Now if you draw a pattern like this, which you should do it as an exercise, you will be getting like this. You see that here, 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 here patterns will appear now.
So basically you're saying the bottom has the diffracted beam as the incident.
Incident beam, that's what is going to happen, because the scattering is very strong here. Each is a very strong beam. The reason is the reason is very simple. If the scattered beam intensity is very small, okay, when it acts as a direct beam for diffraction, the intensity of the diffracted beam will become much smaller. But that is not what going to happen in normal diffraction, because both the transmitted and the diffracted beam has got equal intensity. Because of this, we will be getting a pattern like this. So whenever you get a diffraction pattern like this sort of a thing, there is no need to be alarmed. You know that it is happening because from the top to bottom there is some relationship, and lattice parameters are changing.
So then for the bottom lattice, what would you say is the incident beam direction?
Which
It would
one?
be like there are multiple, no?
No, incident beam direction has not changed.
So the diffracted beam is the incident beam, right? For the top layer of the diffracted
No.
beam is going to be
That can happen even in the top layer also. See, multiple scattering when it takes place, you assume that, see, this is a diffraction. You assume that it's only a one type of a lattice. Okay? This is 0, 0, this is G. This can act as a, that is, and the beam is falling like this. Okay? It's
basically diagonal.
in this. So now this can act as a one and again give rise to a diffraction. When that happens, you can assume that with respect to this as a center you can plot it, but these points will be matching. But that will not happen in this case when there is a slight shift. You understand that? That is how you are able to get subsidiary spots which are going to be there. Even before that one of the first observations of dislocation was that using these Moiré fringes where dislocations are there, you can see that these regions, it appears like the way we draw planes to show edge dislocation. You can see this sort of an effect. But this should not be extended too much because there are hazards associated with it, just qualitatively trying to extend it. But if one works out properly, one can find out whether a defect is there or not. Another example which I will take it is, this is a high resolution micrograph taken from a region where a boundary is there. Okay? Suppose I wanted to find out, okay, whether there is any defect is present, what is the difference between orientation between these boundaries and all. What is the way in which I can do it?
So this is basically that Moira.
No. This pattern essentially is just a normal pattern from a one question. It's like it's from an aluminium. Okay. Suppose I take that this region itself is an aluminium, it is giving a pattern. Okay. Suppose some defect is present. In that region, there will be a slight rotation, like dislocation is there. Close to a dislocation core, the planes might have rotated. Top and the bottom, there may be, because of compressive and tensile strains, there is a small variation in the lattice parameter. But that don't get reflected in the conventional high resolution microscopy. What do? I just generate the same lattice. I take the unit cell, slightly expand a little bit. Okay, the same pattern I can take it, expand it, and superimpose on top of that. I will be seeing a Moira fringe pattern. Na? Correct? Because I said the Moira fringe pattern is a visualization effect. You see it. Now you see this. This is how the pattern will change. Now looking at the Moira fringe pattern, okay, the spacing at which they are coming, okay, we know how much is the deviation which you had given. Now you can calculate back precisely what is going to be the deviation. Is it clear? See, that is because in this pattern, if there is a dislocation is going to be there somewhere here, some planes are slightly deviated from it, you cannot even make out because it is difficult. But if you expand the lattice and put it there, small deviation, now you can generate a Moira fringe pattern and enhance the contrast so that now you are able to see it. You understand that this is one technique which has been employed by scientists when this high resolution microscopy became quite prominent. Is it clear? There are many methods in which it could be done. I just wanted to tell these are all the way in which the result which you get it, you can manipulate it to get a lot of information from the sample, but one should be aware of it. Okay? Because Moira fringe patterns are always seen in microscopy. Okay. Now we will come back to stacking fault. Okay. What is a stacking fault? In FCC, let us take that case. It is the easiest one which has been very well studied crystallographically as well as in microscopy also. What is the sort of a defect which it introduces? Introduction of a fault, what it does? shifting of an atom layer, but what is the fault vector?
In FC,
Yeah, FCC.
1/6, 1/2. 1/6, 1/2 partial.
That is a partial, that is dislocation partial. That is not the fault vector.
1/0.
The fault vector is 1/3, 1/1. That is, in an FCC, along 1/1 direction, if we consider it, 3 layers A, B and C layers are kept on top of one of each other. Suppose I remove one layer. What essentially I have done it? I have created a stacking fault, correct? So if that layer has been removed, now what has happened to that distance? What is the distance which we have made a modification? 1/3 of that distance, correct? In an extrinsic fault, what we do? We remove, we modify 2 layers. So for an intrinsic stacking fault, R will be 1/3, 1/1, and we have to choose the appropriate depending upon which plane and which direction this will change. This is for intrinsic. Our extrinsic will be 2/3, 1/1. Okay, this is going to be the fault vector. Okay, and these intrinsic and extrinsic stacking faults could be created by Frank dislocation, or it could be created by Shockley partials, correct? When Shockley partials create, it's going to be A/6, 1/2 type is the Burgess vector of the dislocation. If it is the Frank dislocation which creates, then the Burgess vector of the dislocation will be A/3, 1/1. I think these things you have studied. If any of you have not studied, I think I will explain now.
Yeah.
Eh?
We just heard the names Shockley and Frank.
Yeah, you are not heard. Okay. Okay, now you look at this one. This is an A layer on top of which, okay, it's a hexagonal arrangement in FCC, right? 1/1 plane. In this, there are some gaps which are there. In this hole, next layer of an atom can come, or the next layer of an atom can come on these holes. Okay. The same type of an atom cannot sit here and here on a hard sphere model, because that spacing doesn't permit. So this is A layer. If this is the position which B layer occupies, and then similar gap will come, and the next layer of atoms, if you put it, it comes to these positions, then we call it as the C layer position. So the stacking sequence essentially become ABC, ABC. Okay. Suppose from here to here, what is the vector? This vector is nothing but, or from this vector will be in this direction is going to be A/6, 2/1/1 from here to here, because you can see from here I had just marked the direction. Okay. From here to here, this vector, this you can calculate it. Okay. If a dislocation with this Burgess vector moves, then what it does is that it moves the atom which are there in B position to a C position. So when a dislocation moves, it moves all atoms on the layers above also, right? So the C position will be moved to the next position. Like that, these layers will be shifted. That means that instead of B atom layer coming, now after A atom layer, it's a C layer comes. This, if we write it as a stacking sequence, it will turn out to be ABC, ABC, ABC. Suppose this B layer is shifted, then it becomes ABC, A. B layer becomes C, C layer becomes A, B, C, A, B, C. Now if you look at this layer essentially is now is a stacking fault which is created. Okay. By shifting a layer, stacking fault could be created. what are the other ways in which the same type of a fault which should be created is that by instead of moving this dislocation, suppose I remove this B layer, then what it will happen? On top of A layer, C layer will collapse. Then it becomes ABC, AC, A, BC, ABC. Now also the same type of a fault is created. But if I remove a layer that is equivalent to a distance which is going to be A by 3 1 on 1, as if that is what the Burgess vector of the Frank dislocation is. So, either having a Frank dislocation or this one, but the same type of a fault is the same, but two types of dislocations could generate the same type of a stacking fault. Okay. By identifying the stacking fault, we will not be able to make out what is the dislocation which has caused it. Only when we analyze the dislocations which are bounding the stacking fault, then we can tell which type of a dislocation caused the stacking fault to occur in the sample. Is it clear? Okay. Now suppose such a fault line is inclined like this and the fault vector is always in this direction. Okay. Now you see that when the fault is inclined, up to this it is there is a phase shift which will introduce because of right. This phase shift is essentially is that as we have written in that expression alpha equals 2 pi g dot r. What is r? R turns out to be 1 by 3. 1 by 3 1 1 1 is the fault vector. So, the dot you take it. Okay. So, alpha will be equal to 2 by 3 into g dot, this is what it is essentially is going to be. Suppose this term turns out to be 3, then alpha will become 2 pi. If g becomes okay, if these two are perpendicular to each other, then it will become 0, then also alpha becomes 0. So, these are all the conditions under which the fault will become invisible, alpha becomes 0. That means that under those conditions the stacking faults will not be seen. But in other condition, for other g vectors, you will be seeing the fault. When we see that fault, then since we know the alpha is constant, okay, with respect to a g value, you substitute this. Now we can try to find out what is going to be the intensity. Okay, this is on the basis of a dynamical condition. When this is a kinematical condition of expression which I mentioned. Dynamical condition when we do it, because here what has to be done is this is for a particular value of x and y. Because if you look at that sample, if I see a sample like this, okay, if I write x, y and z, this is x and y, z is going to vary like this in the sample thickness, right. So, that is how we are trying to find out the intensity which is going to be at the bottom of this sample at every point. Okay. This we have to do it for varying x and y, and then that will give some variation in contrast. And if you see this, the dynamical theory, what the expression which it gives is that Ig equals 1 by s squared, that is the intensity is proportional to the deviation from the Bragg condition, square of inversely proportional to a square of deviation from the Bragg condition. And another is that it is fluctuating with respect to s, correct, s into t inverse, what values they can choose. They can choose a value which is equal to this whole term can become pi, 2 pi, okay, depending upon that the intensities will be fluctuating. So, when the intensity fluctuates as a function of t for a constant s, then what essentially we are going to get it is a fringe contrast. Okay. This is exactly what is happening. That is, suppose we wanted to find out the fault vector. What we have to do is with only one g, we cannot find out the fault vector for any. So, we should know at least 2 vectors for which the stacking fault becomes invisible. Okay. If we know those 2 vectors for which it becomes invisible, then we take the cross product of those 2 vectors, we will be able to find out the fault vector, right. That is what the vector algebra tells us. That is essentially what is being used here. So if you have to choose few different G's, the way in which we can do it is that you go to a Sonaxis pattern, diffraction pattern, you get different spots corresponding to that, okay. Then go to a by tilting the sample in the same region, we can go to a two beam condition. In that two beam condition, okay, we try to image the defects using bright field as well as a dark field reflection, okay. Both the things are being done. If we do that, okay, then we will be getting fringes for various reflections. And one example I will show you is here you see that this is a bright field where it is imaged with a G which is 200. This is a dark field which is imaged of the same stacking faults which are imaged with okay, G200. This is a transmitted beam, that is a bright field and a dark field of the same. Okay. Now you can make out that here if you look at the top and the bottom of the fringe has got the same intensity, but the fringe is there, correct. You look here, the fringe is asymmetric. The top is, one is bright, we know which is top, which is bottom, that has to be found out. There are many methods by which to, and this is one thing which happens. And now the same area, okay, I image it with a reflection 1 bar 1. Okay, that is I go to a two beam condition where the central beam is there, the diffracted beam is that the planes 1 bar 1 planes are the only ones which satisfy the Bragg condition. Then under that condition when we image it, I find that this dislocation is absent, this stacking fault is absent. We are able to see only one stacking fault, correct. Now I go to a G which is 202 bar, that is I slightly tilt the sample so that now the planes which are satisfying Bragg condition is 202 bar planes. When they satisfy the Bragg condition, now you find that both the faults are invisible. Okay. What is the consequence of this? Suppose you do microscopy, okay, your beam is such that the orientation is such that it satisfies this invisibility criterion. You will be seeing no faults in this, but that is why looking at only one direction, like looking at you people only from this angle, I do not get complete information about it. You know, this information is used in common practice in our society. Where exactly it is being used? Where do you do this? For important personalities, when they take photograph, they take both the front and the side view. It's very important persons in society, right? Two views are required because only when you match them, you can get the complete information about the person. So more than one is required. So that is true even in microscopy. Otherwise you will be getting all wrong information. Okay? Is it clear? Okay. Now this is vanishing with respect to, because here it is a mistake, that is why I had just written it here. Okay. Then using this dynamical theory of diffraction, when the contrast has been calculated, that part of it I am just not talking about it because that is beyond the scope of this class. It requires the whole dynamical theory, it has to be taught in our own semester if that has to be done. Now you see that the variation in the intensity, both the top and the bottom it has that same. For the dark field, you see that there is an inversion of contrast which is taking place. So this theory is able to, dynamical theory is able to predict this correctly, okay. And we know that what are the vectors for which these fringes become absent, because this is a stacking fault is nothing but a planar defect, correct. The similar planar defect which we can, no, okay, before we go, suppose one stacking fault is there, another stacking fault forms on top of that, then what is going to be the both the fault vectors together? It is twice that, na? So it will become 2 by 3, 1 1 1. If that is the vector which we use it, when we look for the intensity of the fringes, the fringe contrast will change, because that is going to bring about a variation in the amplitude of the wave, correct. for the same position at which we are trying to calculate it. So, you can say suppose 3 faults are coming on top of it, then what happens to R? R becomes 1 1. That means that it is a perfect translation vector. Perfect translation vector should not give rise to any variation. Now you see that here in between, that is why there are some regions you find that if you look carefully, very faint fringe contrast could be seen. That means that it is an overlapping stacking faults which are there. Depending upon how many layers are overlapping, we get fringe contrast. This also does occur in microscopy when you look at deformed samples. Yes?
Extrinsic stacking fault, vector is 2 by 3 1 1 1.
Yeah.
And we are adding intrinsic 2 them together.
Yeah.
It's becoming 2 by 3. They have a differentiate between these two.
Which one?
Extrinsic stacking fault or intrinsic 2 overlapping.
The intrinsic and extrinsic fault, for which there are some protocols which has been developed on the basis of the contrast, with which we can do that. Okay? And the Burgess vector of the dislocation also has to be looked into it. There are so many things, it is not in one way. No, those part of it, I am just talking about only simple, others I am just explaining it, but not going into the details. If you look into the book Eddington, Practical Transmission Electron Microscopy, there all the procedures are mentioned for identifying various types of defects. Okay? That is what we used to use. Okay. But essentially you can understand that the fringe contrast is going to change, correct? Because what is going to happen is that the dislocations will be bounding this striking fault. Na? That striking fault also will change depending upon whether it is an overlapping striking fault or whether it is going to be a extrinsic striking fault. Okay. There are many cases where you find that in many complex alloys, using G dot B you may not be able to identify uniquely the fault vectors. In such cases, you have to do computer simulation of the images also has to be done. When you have to do computer simulation of images, you should know the full dynamical theory of contrast very well. There are softwares which are written, which are available, like called as EMS package, with which one can do that. Okay. Now, from stacking fault we have talked about it. Let us talk about antiphase boundaries. What is an antiphase boundary? You have studied antiphase boundary? All of you know what antiphase boundary is. So, antiphase boundary is essentially like from one crystal to another crystal when they form and grow. If from one region to another region, the position of the lattice remains the same, lattice positions, but atoms which occupy it, they change their position. So, if we go from here to here, since a specific atom changes, this introduces a fault vector. One in this direction is essentially from here to here if it comes. So, since it is changing, the fault vector is going to be, okay, in this particular 110, okay, or 100. That depends upon the type of crystal lattices which we are considering it. Okay. What will be the effect of this fault vector? As I mentioned there earlier, the first itself, that if we introduce a shift which is T by 2 midway if we between the periodicity of the lattice from one lattice to another, that will give rise to, for 100 type of reflection, the amplitude will become 0. For 200 type of reflection, the amplitude will increase. That is essentially for fundamental reflections, you will not be able to see the fault, but if you image with the superlattice reflections, you will be able to see this. Okay. That is this also gives rise to essentially a type of a fringe contrast, exactly like a striking fault. But what essentially is the difference between them, how it is when the intensity has been calculated for the fault. For the stacking faults between bright field and dark field, the fringes are asymmetric, top and the bottom. In one case it is symmetric, the same type of a fault, dark or bright. In the other case, one is dark and one is bright. In the case of antiphase boundary, first the vectors which we use are going to be different, because there it is some G vectors which we can find out. Those G vectors may not give rise to a striking fault. Like here, if we take 1 on 1 in an FCC type of a lattice, if 1 on 1 is a fundamental reflection, you will not see. but in FCC one-on-one reflection if you do it, quite often you will be finding the fault. So, that is one way to do it. And another is that if we take two vectors for which this fault becomes invisible, we can try to identify what the fault vector is, because that two G vectors which you are taken, cross product of will give you, you used to find out the magnitude of the fault vector. Is it clear? And another is that the intensity both in the bright field and dark field, it becomes symmetric. All these things are given in that book Eddington. Okay. But what I wanted to tell is that there are all planar faults give rise to a fringe pattern. They look quite similar. So, when you look at the fringe pattern, now you have to identify whether it is a stacking fault, whether it is an antiphase boundary. Okay. So, this is like this. Here if you see it, these are two types of lattices which are being shown. 110 is the interface between them, okay. And in this the C direction is here, in this C direction is here. This is like a twin related. Generally in these sort of lattices, okay, the C by A ratio need not be exactly same. C by A ratio can be away from 1. So, if that is the case, that gives rise to from one region to another region. From here, if C is like this, when we come here, if C by A ratio is different, this will give it a small variation in S. So, as I mentioned it in that formula for Ig, the variation in S also can give rise to a fringe. Okay. This will give rise to, now you see that when a domain boundary is there between two domains, there is a fringe contrast which is coming. Okay. This also looks like a stacking fault contrast. Okay. And like this example, if you take it, here this is a boundary which is a domain boundary. This is a stacking fault. Okay. We could differentiate this because we try to do a detailed analysis to find out which is the stacking fault, right. Otherwise, can you make out from this one to this one which is which? Looking at it, you cannot tell. Unless and until you do an analysis, you will not be able to identify it. So, just doing microscopy, that is what I want to tell is that in an electron microscope, because of dynamical interaction of electrons, especially the interference of the electron beams, which is giving rise to a contrast, unless you understand what the interaction is and how they can give rise to contrast. Okay, this has been all done and given in some books also. Unless if you have to simulate it, you should know the theory much better. Okay, there are many situations where you have to do all the simulation as well. Okay, this is essentially a thin precipitate. If I take it, the precipitate also it may be 1 or 2 layers. That precipitate, what it does, it is the beam which enters here to a beam which comes down. It may be introducing only a small phase shift. If such a phase shift is introduced, that will manifest itself as a fringe contrast. This is one case which comes from a precipitate. Here also you get a fringe contrast. So, there are various reasons why you get a fringe contrast. So, all fringes are due to some type of a defect, but which type of a defect, if you have to identify it, you have to do a detailed analysis. At least for the defects like stacking faults, if you know crystallography, if you take FCC, you know what all the types of fault, stacking fault which it can form, what is the fault vector you know. Similarly, if you know an ordered lattice, immediately you can find out what all the vectors which are going to be the antiphase boundary vectors. Like antiphase boundary vectors are like whatever the crystallography which you have studied, there are some symmetry operations which are there, right, symmetry elements. When it goes from one lattice to another lattice, and these symmetry operations are, it could be translational symmetry, rotational symmetry, mirror symmetry, all are there. Okay. When from one lattice to another, when the space group symmetry changes, that means that some symmetry elements will be lost from the other lattice. All those symmetry elements which are lost, they appear as defects in the ordered lattice. That is, translational symmetry elements will appear as antiphase boundary, which are lost, and the rotational ones which are lost, they will appear as domain boundaries, and all of them will give rise to, these are all planar faults, so they give rise to essentially a fringe contrast. Okay. The next part is imaging strain. Okay. That we will do it in the next class. We will stop here.